This is more than a classical mechanics class. How many people have read the preface? Just out of curiosity. 1, 2, 3, 4, 5. As you can see from that, but I'll say it again, we're going to be making a connection between classical mechanics and quantum mechanics quite often. But in just the last few weeks, a very good friend of mine has finished a book called The Semi-Classical Way. This is the autographed copy right here. And we have a second Advanced Mechanics number 2. That would be the main text for it. And it is so many new things that are in this book and explained very well that it's really worth getting it. And TC here, who is a tile reamer, who is a secondary source for you to call, email when you have questions about the class. He actually got his PhD from me in 1999. And so make use of his skill, particularly his skill with regard to the cyber part of this class. So
direct all those questions to me. Anything that's IT related in the background.
Now, we're going to dive in right here, and what I want to do is make a very logical a course out of this, and Elkins Razor is to be used as much as possible throughout this thing. We're going to start very simply. We're just going to start with a very simple idea, maybe a tragic idea, but nevertheless a simple one. Two things colliding with each other, but I'm thinking of a freeway collision. So that's what we're going to analyze today, both algebraically and geometrically. And that's really what this is all about here. Keep the number of axioms down, make them simple. That's the Elkins Razor idea. And then derive from that is what we try to do with everything we teach in this room. So the very first 2 pictures here, and I'll try to keep these 3 screens here more or less coordinated, since we have a record-breaking class here of 13. We'll attempt to make it easy for everyone to see what's going on. Now, a lot of this class has animations, and this is no exception, just this first picture here. But let me tell you the whole idea here. We have a 60-mile-an-hour self-acting 4-ton SUV that's the protagonist and villain of this story. And he's looking at his screen scan, you know, like this, going 60 miles an hour on the freeway, okay? And there's this head case right here in a Volkswagen. This car very much similar to the one I got when I first graduated from college, putting along at 10 miles an hour. And there's going to be a collision here. And the question is, what are the velocities after that collision? That VW putting along at 10 miles an hour, SUV racing along at 60. So that's the problem we're going to solve, using it to set up this whole course. We're going to be deriving the beginnings of a Lagrangian by doing this. So the animation, just to make sure that you see, there are 2 extreme cases here. The elastic case, which is this one right here. And here we're doing a plot in space versus time, which you'd be used to if you take a calculus course that had physics at its thing, and UP course would have that all the time. The other way to do that plot, and back here, is, and this is the elastic case again, but this is the one that we're going to really use in Unit 8, where we actually derive relativity and quantum mechanics from very simple ideas, and also simplify classical mechanics in so doing. But this is called a Minkowski plot. All we've done is switch x with t. And Minkowski would like to have the time on that plot. We'll talk about that much later in the course. But there's the situation that would probably not happen in the freeway. On the freeway case, it would be more like this other extreme. And we'll use the Minkowski diagram for it as well. This is the more likely situation if it's a direct collision. This is what I call a crunch. And that is these two masses become one mass. Totally inelastic versus the other ones are totally elastic. And of course the real world is in between that. And we'll talk about that at the very end. Okay, so let's go ahead here with the logic that we need in order to make progress on mechanics at the very beginning. So that would involve the idea that you already have in your heads if you've taken any physics classes at all and had to solve a problem like that. And that was, as a conventional solution, to look up the usual momentum and energy formulas and solve. Okay, so you have basically a quadratic equation to solve. Okay, now I want to say we can do this more easily with just really one axiom, but you're going to see later we need 1.5 axioms to build the mechanics that we'll need for this course. And that axiom is that all masses or masses in this collision keep their total momentum until it's changed by some outsider. Now, a lot of you will end up in some sort of university setting, I would hope. I would just, because I like those kind of things, being a nice ivory tower. And you'll probably teach a course that deals with this. And so one of the things you can get from this is a really simple way to start mechanics that is sort of unique to this laboratory here. So we must make a point that the collisions involve a very violent change in velocities, but not the total momentum. That's the axiom. That's, for classical world, an unprovable axiom. It's not until you actually start doing quantum mechanics that you figure out how to quasi-prove this axiom. More about that, as I said, much later. But the basic idea of all of this is to, as I say, use Elkins Razor and this unconventional way of deriving the quantity of energy. That's what we really want today. But also just the basic mechanics of a collision is with a simple geometry, a simple idea of geometry combined with algebra. So I point out Occam's razor stated 3 different ways. Okay, don't make pluralities of conjectures without necessity. That's the direct translation of the Latin there. Logically, it's assume less, prove more. That's really, for a theorist, that's the most important thing, I think, that I got from Richard Feynman when I was a graduate student, first learning from him. And the practical coding advice, and this is the cyber world, keep it simple, make it powerful. So this whole idea is going to, I hope, be adhered to as much as possible throughout this course. So here we are with the momentum before, and the momentum being the product of the mass and the velocity for each of these 2 objects, the VW and the SUV. Now some of you are foreign students. I want to make sure you know what I'm talking about when I say SUV. There's plenty of those around, right? How many people are sure what an SUV stands for? Please show of hands. How many are questioning about what SUV stands for? How many? Anybody? Okay, good, good. Anybody else? Okay, it's sports utility vehicle, right? The worst of them being the Hummer, right? Okay, that's even more mass than this thing that I'm drawing here, but it's kind of a Hummer-like. Okay, now VW, everybody knows what that? The Volkswagen. Okay,
German car.
and they now make them more rounded than that. Okay, so That's what we're dealing with here, and we're going to be using those subscripts in our equations for a while here. Now, this sort of a very simple expression here. If we add up 4 tons, that's how much this SUV, particular SUV, that's a very light SUV, by the way. And then 1 ton, actually Volkswagens are a little bit more than that, but the one I got was just about that. So 4 times 60 plus 1 times 10 is 4 times question mark, that's final, and question mark for the final velocity of the VW. Okay? In any case, this is supposed to be a constant. This adds up to 250. That's our axiom. That's all we're going to assume. We're going to try to get everything in this course practically out of that axiom. Now this is just a Cartesian equation. Let's honor René Descartes for making graphs. Graphs are really powerful ways to show what's going on here. And I've already shown you a moving graph, which is something that I'm sure Descartes would love to have had. And of course we have it all the time. So here's the basic situation, and this is what I want to make a plot of, and that's what I've given you some graph paper for. And I'm going to do my plot up here while you do yours on that piece of graph paper. And basically what we're going to have is the axis that describes what's going on with the SUV, the heavier one is hanging down here at the bottom, going at some speed, 60 we said. So that's the point there. But let's just make sure you label this down here what it is. It's a velocity sub SUV. And the numbers are already on your graph. The graph doesn't quite look like this. You're going to be working in the center of that graph and outward from to the right of the central axis. And what we're talking about here is a speed of 60 miles an hour for it. And then up this axis right here, the VW speeds, it's just loafing along, enjoying his grass or whatever, 10 miles an hour. So this is an axis that is, and I'll just put it right at the very top here, this is kind of crowded here, velocity sub VW. So I circled it because that's the thing. So we're going to be starting our we're going to be going along happily, at least for a while, until we move off of this point in the collision. Okay? And our axiom tells us where we're going to be moving. We're going to be moving along the line that keeps the momentum constant. That is the simple linear equation that Descartes would like. So, what we do in order to do that is draw a line that slopes with the ratio of their masses, actually negative times the ratio of their masses. So from this point right here, I'm going to ask you to just take your ruler and draw a line that has the slope, and it's going to be 1 unit this way and 4 units this way, then another unit this way and 4 the other way. So before you put the ruler down, go ahead and put a point at, first of all, 1 unit to the negative, this is going to be negative slope, and then 1, 2, 3, 4 units to the positive. Okay, and then do it again, 1 unit negative, and then 1, 2, 3, 4 units positive. Okay, so that is going to be the line on which the momentum, if you can think of momentum as something that's changing, and boy, it's going to change really fast when the collision occurs, but when we're done, it's going to be somewhere else on this line. Okay, now it might be on the negative side if something really weird happened, but that's more like it. Anyway, draw the entire line with your ruler as accurately or as you can on your graph. And that's the first stage of this geometrical construction, a solution to a linear equation. The equation's not really linear, it's quadratic, but this is a start. Okay? So there's what we call a momentum line, this thing right here. Before collision, during collision, after, where? Where is that final point, you say? Okay, so that's what we're after. Now we have to decide which of these two cases here do we want to take. And for the first moment here, I'm going to take the totally inelastic case, where when we're done with a collision, these two 1-ton and 4-ton objects have melted into a single 5-ton object. Okay? Now, at this point, you have a quick question mark about where that's going to be. Okay? And geometry is really quick at telling you something about where that's going to be. I'm going to get this up on both screens so I make sure. I'm good at using 3 screens quite yet. I'll get better. So, idea being that they are going to be one mass after this collision takes place. Okay? So where on this curve would that be? And the clue to that is to simply draw, and I'll get my magnetic ruler.
It's stuck.
There it is. And looking where it would normally be with the magnet will make it be anywhere on the board. So let's use it. I'm going to draw a line where the two velocities are equal. That is, the SUV is the same as the VW. All along that line, that is true. So just draw it, and if you have a red pen, that would be nicer, because we're going to use this red line for a lot of things. But that's the velocity equal velocity line, right? Okay, so where is the end of this collision? That's the key thing at this moment for this particular thing. So we're trying to figure out where the collision is going to end up. And that is the answer right there. That's the final crunch. Very obvious geometrical step, if you think about it a little bit, right? Okay, so we're going to put it up on this screen here as well. Okay, now, the next one we'd like to find, and this is where it gets a little funny, but it's the logic that we really need for this whole course. Where is the final kabong? The kind of collision that you get if these were parking lot speeds, where you didn't damage the cars. The other one would have totally destroyed one of them and probably did irreparable damage to the other at that speed. But in a parking lot, if I was talking about instead of 60 miles an hour, say 60 feet per minute, that's hardly moving, right? Then the cars would not be damaged. In fact, it's a law, used to be a law, that cars had to not take damage at 5 mile an hour collision. So that's what we're going for here. And this is where the compass comes in. Because what I need to do is draw a circle around this crunch point right here. And I'll go ahead and do it. But later on, when we do a lot of these collisions all at once, we're going to have to speed this process up a bit and not draw the whole circle. Mainly, I'm going to swing this thing over and get the answer that's right there. But let me just go ahead and do it. And I'll only draw the circle on this side, okay, just to indicate where we're going here. And I'm ending up just a tad below where I was because the thing slipped a little bit, but that's what we need at this point. So there's our end point for a totally elastic collision. This is our end point right here for a totally inelastic collision. Now, for those of you that might have thought of going to engineering school instead of physics, you would, if you were a civil engineer or a marine engineer or aeronautical engineer, central points, center of things, center points, are usually indicated by a little circle with a cross and half 90-degree quadrants colored, usually in some color like yellow. I should have used yellow here, okay? But bear with me. That is what we call the center of momentum point. That's this thing we'll be referring to as COM. Okay?
Can I ask a question?
Yes, please.
So why did you draw the semicircle again?
Okay, the reason and a very good question. The reason we drew that is because we need one more half axiom in order to pull this off. And that half axiom is called time reversal symmetry. Okay? In other words, this collision is you can undo it. So what's going to happen with the crunch is you're just going to go in and you're going to stay there. But if it's elastic, you go in and you come back out again by exactly the amount you went in. That's the idea. That's what it means to do time reversal symmetry. And a lot of things in quantum mechanics are perfectly this. But in classical mechanics, even if I do parking lot speeds, you're still going to leave a few atoms behind, and some are going to be vibrating, and it's going to be a different state than you were, just slightly different, right? In quantum mechanics, you've got this perfection of the wave behavior that we're going to emphasize when we get to Unit 4, and then some stuff after that. So, this is all of the thinking we have to do. Now we just have to sort of flesh it out. Using some algebra, now we get a chance to look carefully at the algebra that would go with such a geometry. Okay. Now, any other questions before I push on? I'll push this one on right away, because I think this is a drawing that you ought to do. Now, the homework that I've assigned, and it's already, I think, been put up on the web, and I was trying to make a copy of it for paper, and if you stick around after class you can pick that up, but I don't have it right now, and in case it's available. And the first problem is to simply finish, as we go through this lecture, we're going to do the finish this, and then also connect it to the algebra that goes with it. But anyway, the first thing is this circle, and then the other thing that we do, and this I think is really important in the physics business, is we draw a vector to represent the velocities, the initial and the final velocities. So we might as well go ahead and do that. Whatever color you want to use, say green for go. Well, I haven't handed out colored pens anyway, and I won't require that for the thing that's the homework. But this vector right here is pointing with a thing that we're going to be calling Vn. This is the vector V super or sub n. I just write it V with a capital I-N. That's initial. And then for the elastic collision, that vector, I can put little arrowheads on this thing to make it look physicky. But as I go for this one right here, this is the way the heck it's a much longer vector. And while we're drawing it, let's be aware of what has happened to the poor VW in this elastic collision. 90 miles an hour? Is that survivable? Maybe not. But you get one of the lessons of this is that the reason car accident deaths have gone down so much in just the last 10 or 15 years is that the cars are designed by engineers, and that's a really terrible line that I'm drawing there. Got the chalk all over the thing. But this is V fin, okay, that we'll be using in our equations that we write. And this will be a good place for us to introduce vectors and matrices that we'll use for other things. But quantum mechanics, of course, is full of them. So the secretarial work for quantum mechanics is based on that. Now you can go ahead later on and finish the parallelogram here, but everything has to balance. This distance up to that point would have to be the same as the length of the center of momentum vector, and we might as well get that one on here right off the bat. And I'll pick out a blue color for it. So you do want to get this vector in the collection of vectors here. It is a very important one for the algebra that we're going to be doing as we go through this problem analytically. Okay, so far so good. This being V initial down here, the actual point, and that's what's important. The line doesn't necessarily mean much at first, and this one right here, V fin. And then, of course, the one in the center here, this vector, is V COM, center of momentum. Okay, so that's about as much in drawing as we're going to do for this particular, but I'm asking you to put other things on this, and we'll be seeing what those are as we go along here. Okay, so there's the really important equation to take advantage of in this beginning of the development of this algebra right here. And one of the things that should be pointed out about this construction is that what we're diagramming here, and this is used for a lot of things in statistical mechanics and physics, that is the weighted average of two velocities. Okay, weighted literally by a mass 1 and a mass 2. Okay, number 1, a guy being this heavy SUV, 4, and the number 2 being our little light Volkswagen that has a mass of 1. Okay, so when you take the conservation of momentum equation and have the total mass here multiplying it, that's the momentum of the whole thing, and divide that into each of these, you get expressions for weighted averages. A weighted average for this point, a weighted average for this point, and a weighted average for this point, all being equal. Okay, that's the axiom 1, conservation of momentum, at work, making some mathematical expression. Okay, is that clear? Because this is what we're going to base all of our stuff on. It gets us kinetic energy. But I also want to, while I'm doing that, I want to really make sure that this vector notation, which is kind of weird, is understood clearly. So I have to point out that what we're doing here is pretty weird. That's what this room's all about, being weird. Okay? But weird smart-like. This is crazy fox-like. Okay? This vector is not the usual xy component of a velocity. It's SUV, VW components, right? It's different particles being used as subscripts. Okay? We don't have x and y components of these vectors. They're all along the freeway. This is one-dimensional, right, as far as moving. Okay? But we got to get used to phase space being position and velocity. Okay? That's what mechanics is really made of. And quantum mechanics too, except it's position and momentum usually are the canonical pairs that you work with. Okay? But in any case, I want to make that clear. And of course, here are the vectors in the usual way that you would write vectors x and y. Well, not necessarily. You used to giving coordinates like x and y, right? Just x, y. You write that, right? Well, this is a cat, that's a bra, okay? These are these weird things you use in quantum mechanics all the time, right? Invented by Well, Dirac is really responsible for that, as far as I can tell. In any case, we want to do things with those vectors that help us with this particular problem of taking this. I better get my things up to speed here. This is the first thing that they do, is make dot products. Okay. Dot product between a bra and a kit. The secretarial rules are fairly simple. There's the outer product. I'll get that in a minute. Here's the dot product again. So vfin dot vn is a number that we're going to be kind of interested in here. Just the dot product with two difference. But also the vfin with itself and vn with itself. They're all going to be important here. So when you look at this, you have to say, well, not too weird actually. This starts to make sense as a secretarial, more powerful way to do things. Okay? And while we're at it, we're going to also be interested in the outer product of this. Outer product meaning, instead of putting the bra and the kit flat side to flat side with the 2 points on either side, we put point to point. Okay, this picture right here, in fin. Okay, what we mean is a column across a row in such a way that we put this times this there, this times this there, and so on in a lexicographic order, and make a number with a matrix with some pretty large numbers in it that will have significance shortly. But this is something you do all the time. You make quantum operators. They're all made out of kit bras. Whereas the scalar products are made out of brackets, and that's where the name comes from, bracket. All right? Okay, so I want to make use of that in the problem that we're doing. But let's pause and do something physicists has to do by law. Some kind of law is out there that says you have to state that the model you have is idealized and what goes with that, the fine print that goes with a model. Okay? And what we've got here is just one dimension of a highway, and we're ignoring friction, rolling friction, all kinds of frictions, except the actual resistance to collision does play a role here. But other than that, we're constraining these cars as though they were on an air track. And of course, that's the best demonstration of mechanics without friction that we have, unless you have a superconducting track, which is really the best. And liquid nitrogen is all you need, and some very fancy magnets to do that. In any case, I want to just quickly say that in units 1 and 2 particularly that follows this, we'll be talking about translations in 3 dimensions, and we'll also in units 3 and 7 talk about the 6 rotational degrees of freedoms that U, S, U, V, and V. There's 3 for each of them, just as there are 3 translational dimensions for each of them. This machine has been put here to take care of the angles that you have to talk about, Euler's angles, and get you to understand them. And then they have quantum mechanical implications. And finally, these objects have enormous numbers of vibrational modes. Then they have just plain fall apart coordinates for all of the atoms in them. That, of course, is taking this thing well beyond anything that you can calculate most of the time. But there will be 12 rigid body degrees of freedom altogether if that's all we have to worry about. And then whatever you have. So if you have an N atom molecule, it has 3N minus 6 degrees of freedom is the word you'll see talked about when this is done. Okay, now let's do one more thing, talk about the symmetry aspects of this highway disaster that we're talking about here. or parking lot experiment, which is not so disastrous. And that involves looking at what Galileo has given us. And Galileo has said, and he's lived in Genoa, where there were sailboats that came into the harbor, and he's so wonderfully traveled, seemed frictionlessly and constant speeds. And he realized that if you increase your velocity by, well, he didn't say 50 miles an hour, that would be nothing went 50 miles an hour, no horse could go 50 miles an hour. But I'm just putting it down as an example. The rest of the world appears to be 50 miles per hour slower to you. So you guys, I'm say I'm some kind of coach, and I'm angry that you're not moving. One of the things is I can convince you to move at 5 miles an hour that way, or I could just simply walk 5 miles an hour this way. Now I've accomplished that goal, right? You're all going 5 miles an hour that way. Right? That's what we're talking about, right? Relativity of the Galilean type. Okay, and that's his idea right there. Is that everything appears 50 miles per hour slower. Okay, now on the graph, what does this amount to? How do you show this on the graphs that we're doing, and on the graphs that you have on the homework that I've given you on the web? As I said, I should have had it ready to print. But the idea is, if you want to see what it looks like to somebody in a center of momentum thing, 50 miles an hour makes it go boom, like that. So what, this point right here, it used to have a speed of 50 miles an hour, now it's speed 0. Okay? So there's the geometry of the Galilean transformation. That's all there is to it. And the idea is that, of course, it's like some direction x, y, or z, and we're talking about being slower in that direction in particular. That's not something. Now you can ask the question, Sir, Mr. Galileo, he looks very wise with all that hair, does that include a light pulse? And the answer is, well, yeah, kinda. But of course you know the answer that Einstein gives in 1905 is not at all. You do not take 50 miles an hour off of a light pulse. No matter how fast you go, you don't take any of those miles an hour off. Okay? But this queer thing about light, that it seems the same by everything, I mean, that's what's really mysterious about relativity, that we try to find ways to understand later on. But it's really quite mysterious. There is something with a finite speed that is not affected by your motion. That's a mind-boggler, right? Real mind-boggler. He gets to say it because the speed of light for him is infinite. You subtract 50 from infinity, you've got infinity. It has not changed. Now we're talking about light with 3 times 10 to the 8th meters per second, right? We're talking about when you say per hour. Okay, if you take miles per hour, we're talking about trillion miles per hour. So you really have to go fast in order to worry about this at all. But be aware that here we just draw a line moving back and forth on a velocity chart to show all of this. Okay, now here's a bunch of cases. I indicated 5 of these have 0 for a velocity coordinate, so that would be a starting frame for the VW. This one would be a starting frame for the SF, or a final frame for the SUV, and so forth. So any one of these lines is a different reference frame describing a collision. But it's essentially the same collision. It's being looked at differently. And that's an important thing to keep in mind here. And as we go through and make this more complicated, and then look at what's the symmetry that's associated with this thing. So let me just go ahead with that one right there, where we talk about the time reversal symmetry. Time reversal symmetry being where you simply say I'm turning all the velocities from whatever value it had to negative that value. That is, I'm going to reflect through the origin. That's an inversion operation on this crazy graph of VW versus SUV. And that's what we really need to understand, because as you change from here to here, and actually you'd be going down here if you were talking about something that's not a center of momentum. But if you're talking about something that's in the center of momentum, it's really easy. You simply just flip it through there. And that's basically what we're saying about that. Time reversal means flip t to minus t, run a movie backwards, and of course, when we think about running a movie backwards for a collision, when a collision happens, you see crumple, crumple, smoke, and all sorts of stuff happening, right? And then you play the movie backwards, and here's this pile of wreckage, right, that reconstructs itself. All the smoke goes back in there and makes a new car going either way, and a new SUV on this side, right? So what we're asking here, in order to get the conservation of energy, which is what the goal of today's lecture, is to get that, then we have to think about this particular symmetry of reversing time. Now, real quick here, the vector algebra that we're going to be using in order to accomplish this, first of all, there's a usual notation using the 2x2 matrix, and then a column vector, a ket, and then it gets a new ket. This is all stuff that you should have down. Direct notation in some ways is much simpler to write, except when you really put in the details. Then it's a little bit more complicated. You keep making these little lines for the kets and the bras. In any case, we're going to be doing that, so it may kind of look a little complicated, but the ideas, I hope, will be very simple here. So we're going to start again with what we had. Now, be aware that later on in this course, we're going to have a generalized expressions for relations of momentum and velocity that are still linear, but they have off-diagonal components. Where do you run into this? A lot of people are going to be working inside crystals and solids, and there you have effective momentum, effective group velocity relationships, which are not just diagonal matrices. So get used to that. Get used to this not being zero, but for today we're going to pretty much stay with the usual situation where those are zero. So there's, again, 3 ways to write our axiom 1 here. And once, at this point, I should point out that this P total isn't really, I mean, this is a kind of a weird momentum, the total mass times the velocity of the center of momentum. Okay, so COM could stand for center of mass. And what we already noted is all the different components of VCOM are equal. They're both equal to 50. That's this component, and this component is exactly 50. So we're going to take this apart and put it into an equation. And the off-diagonal M12 and M21 will be 0. I'm just putting this up to you to get you ready for what will come later. Many dimensions. We're talking about rotations. This is going to be an inertia tensor to relate angular velocity to angular momentum. All kinds of things that use this sort of skullduggery with matrices. So let's rewrite this thing using the matrix forms that we have. This one right here, if I go the product of VCOM times, and the thing that I have here is really M dot Vn. That's what that is right there. And then right next to it I have this thing. That's the M matrix, that matrix right there, times the V fin. And then, oh, don't forget VCOM, M times that, okay? And this is supposed to come out to be a number that actually has the VCOM at twice. This is an mv squared here. And you already know the formula for kinetic energy is half of that but pretend you don't, and that's what we're working on here. So the numerical details of this are key to getting a feeling for what's going on here. Now this thing, this velocity times momentum, that's really important. That is what we call action. And that's something that the Rick Heller is just nothing but action in this book. Okay? Very important part of quantum mechanics. Joule second, that's the h bar in quantum mechanics. So this is what we're dealing with. We're dealing with some action expression involving these tensors, and this is it written out. And I'm asking you in your homework to go ahead and work this out for quite a different problem. So that's the hard problem, number 3, for this coming week. Now, this picture's been here all along. The points of the vectors, VCOM, Vn, and Vthin, if we get to have time reversal symmetry, are all on the same line. That's a key thing here. And also, and one thing that's really important, if we're going to have time reversal, the time reversal axiom really comes down to demanding that the sum of this vector and this vector times 1/2 is equal to this vector. That's the time reversal half axiom, okay, that we need to reflect a collision in which no damage is done. It's reversible in time. Okay? We come out alive, and our bank of crowns are also alive. Whereas, if it doesn't make it up there, or it ends up in that pile in the middle, you're either dead or your bank account is dead. Okay, so here is just going ahead with that total momentum of 250. Now, what I've done here is just go ahead and write this thing out, but I'm using the n here, the fin here, for these two equations, and then just the fact that when I put this all together, I get that particular number, which is 50 times the total mass here of 5, and then another 50. So it's the 12,500 is this expression for our well, it would be this axiom, this action right here. So when we write this thing out, this is one way to say wherever I see a VCOM, I'm going to expect the time reversal demands this. This is, I guess, axiom 2 is what a good thing to call it. Okay, so once you do that, then you get this funny thing on this side right here, and then you do it again with that one, okay, and then one more time, but with both of them. Okay, so then you take it apart. Okay, 1/2 goes here, 1/2 goes there, same thing there, and then this thing, it would have a whole bunch of terms. I haven't bothered to write them, but the tensor algebra immediately lets us express it. Now, first of all, you have to note that even if I had off-diagonal components here, if they were the same, that is, if this were a Hermitian matrix, this thing was Hermitian, like quantum mechanics demands of all observable operators, then I have the same result that I'm getting here with zeros there. So these lopsided FLN terms turn out to be equal. Now, I'm not keeping up with my different screens here, so I can get this one up to speed here. This thing goes really fast, so I can afford to, leave the details behind here. That's the bottom line on that one, and then this is the bottom line for this one right here, where we actually end up with a proof that kinetic energy is a constant, what we call kinetic. We derive kinetic energy. We don't just pull it out of a hat. And that's, I think, a good thing. But it's based on having a mass matrix that is symmetric. Well, one that's diagonal is nicely symmetric, thank you. but doesn't have to be. These two numbers can be equal non-zero numbers, and this will still work. Okay, so that's the main thing I want to show today, and the main thing that you should be rederiving for a more complicated collision on the homework. Now let's again, after we've done this, this is just going ahead and writing the actual values of the initial kinetic energy, 1/2 mv squared basically, and the initial final kinetic energy, and that's total kinetic energy. They both come out to be 7250, a wonderful thing, right? That's the basic thing that this proves here. Now you see there's something that's not so comfortable about this if you were going to be using it on, say, high school students. But high school students should learn about matrices early. And this is a good way to do it, I think. I haven't tried it yet, but maybe you can tell me how it works out if you take one of these positions where you do a little bit of teaching on the side. Okay, now here's the thing that really is going on with this, and that is that the vectors that we've all been putting down here, two of them sit on the constant kinetic energy ellipse. So this is a quadratic expression. This KE in or fin, initial or final, they both land on the KE conservation ellipse. And this is what I'm going to be asking you to actually draw and to understand a little bit of the geometry of this. This is really quite non-trivial geometry that I didn't see in any high school geometry books, but it should have been. And it's easy to see that this has the algebraic form of the ellipse with a semi-major, that is major radius and minor radius, A and B. So it just behooves one to go ahead and work out what the numerical values of those things are. Okay, and in this particular case, it's a radical involving the kinetic energy with divided by m/2. First, the mass of the SUV, and then the mass of the Volkswagen. So the Volkswagen, with its mass of 1, let's get this one coordinated here. Oh, I've gone too far. This one right here, large, 120. Okay. Now you see, one of the things that I think it's good for students to do the actual geometry to derive something and realize how precious it is to have 2-figure precision. And 3, wow, that's really amazing. Anybody that works in a lab probably already has that feeling, but you know, students sit there with 13 figures on a typical calculator, right, and figure, oh, there's nothing to 13 figures, right? It's a heck of a lot of information, and you should appreciate it. Okay? And you should also appreciate what my cohorts at Jilla have done, and that is make oscillators that are true to 18 figures. 18. We're taking spectra in 16, 17, 18 figures. It takes you a long time just to write down the first number. And you've got 200 to go. So we're definitely computer age to make computers do this work for us. Okay. But still, just thinking about having here 4 figures, I'm not going to get that from my geometry. I'm going to have to use algebra. Okay? So, this gives you that little lesson. But also, it's kind of interesting to see what happened during that collision. It leaves the ellipse and is sitting here with less kinetic energy than it originally had, and then it regains it and gets back to the ellipse. Perfectly, if it was a time reversible thing that satisfied axiom 2. Okay, so just to make that point clear, we have some demos here that we'll show you, and this will give us a pretty good picture of what's actually happening. And I'll get this one up to speed as well. Now, one of the advantages of doing all this stuff electronically on the screen here is, and I do treasure questions. If you want me to go back, we can go back, right?
I do have a question.
Yes. What would you like to go back to?
Do A and B have any like significance? Do they mean something
Mhm.
special?
Mm-hmm. That's a really good question, and that's what you should ask about anything, right? Let's get one here that shows A and B pretty clearly. That's not it. I guess that one shows it clearly. Well, basically, what you're asking is, what's the meaning of this particular point right here? Well, that's a possible state for this system. It has the same energy as any of the other two that we've been talking about, right? And so you might want to start with no velocity on the VW. Let's make him not just be going 10 miles an hour, let's make it with no miles an hour, right? And so what you're talking about is the energy that would be associated with the SUV entirely. Okay. And whatever ellipse goes through that point, well, the next thing to do is just go a line parallel to this and wind up there. That's what would happen if you hit the stationary one. What else can I say?
So
One
A
thing
and
to
B-
notice is if the two of them have exactly the same velocity, that is of the CLM, right? And they would be here, right? And the line that connects initial and final, which would now be on top of each other, would be a tangent line. So what's really cool about this geometry is it's telling you that all of the collision lines, which have to have this particular mass ratio as a slope, right? All of them are bisected by a 45-degree line. That's probably not what you're looking for. That's a geometrical sort of, oh yeah, aha, right?
Yeah.
Now all of these lines that have the slope square root m1 over m2, a to b, right? All of them are bisected by this. At the moment I can't say any more, but and of course you'd have a situation where you went from here to some point down here, right? And let's do that. I mean, that's what the animations are for. It's so easy just to run an animation and not get chalk all over your hands or ink on your hands or sawdust or whatever is there. Let's just run this one. This is a basic elastic collision, which we've already seen. Let's just remind ourselves of that. Now later on we're going to be throwing super balls around here, and this is a typical collision right here. Bang! That's the collision that occurred. And somewhere is a 45-degree line that bisects that. Okay? Now, what's powerful about the methods that we're using here, the matrix methods that we're using here, which will eventually generate symmetry methods, is if I resume, this thing comes and scoots down there, and then scoots down there after a collision. And remember, nothing moves over here until a collision occurs with either the ceiling, bang, right? And it gets bisected by that one. And then the two are one of them's chasing the other one, but he's not going to catch him before this one gets down to the floor. And when it gets down to the floor, it's going to change that dimension and be bisected by here. And then we're going to have another collision off of that point. Bingo, right? Now after you do this a few more times, like maybe 100, you will get a nice ellipse. If this is an ergodic system, a system that takes advantage of its velocity space. And we're only plotting a velocity space, you see. This is all being done with velocity plots and velocity algebra. We haven't mentioned where these things are on the highway. That is not important because we have a spatial symmetry. And here's an example of where you're going to see that this thing is not going to be ergodic. This 1:4 ratio is just going to reproduce this. So there's a symmetry right there that we need to investigate. Okay, so this is where you take mechanics and make it from a stupid, dull bunch of crap into something that's kind of interesting, and you can think about things to do with it. And that really is the goal, I think, of this room, is to take the dullness out, if possible. It's not always possible. Okay, let's go ahead here. Now, I am running an hour right now. We've got a few more minutes here where we can play with some things. I would like to maybe take a look at, let's see if I got this right here.
You, in essence, just ran that one. You let it go.
This one. This one is just the old thing where we actually show them doing it on the velocity plot. Okay, so you can, not much we can do right there that's I think of interest at this point. So let me come back here. And let's take us to a case, this particular one we'll see in the next lecture, where you fill up more of the velocity space. But once again, very often, it finds a way to repeat. And this has an interesting history. Right after the war, at Los Alamos, refinement was working, and there was Fermi there too, and a guy named Pasta, and then Stanislaw Ulam was the real brains behind a lot of the nuclear work. And they were always wondering, is the statistical mechanics really correct? Does it really happen that the coordinates or phase variables for a molecular system, say, or an atomic system, is it really true that it uses all the available phase space and does so with probabilities that can be determined by KT and the energy associated there too? Is that really true? So they started making models where they could do it on a computer, equations that, there are no ways, they're very nonlinear and couldn't solve by hand. And the first one was just to move a ceiling and have something bouncing. And right away it just went crazy. Did funny little patterns, and just looked like you're going to the statistical mechanics. And that was the beginning of the whole science. It's sort of a quasi-science now, but the science of chaotic mechanics, where you have a very simple determinant descriptor, and you get randomness. What looks like randomness isn't really random. If you run it out to 28 places, oh yeah, it's right on. But then it starts to eat up on the 29th place, and then the 30th, and then the 31st, exponentially degrading. So then you have to have 60 places in order to predict the weather. And of course, nobody can do that. So, the idea is you can't predict the weather. I think borne out in the last week pretty well. Okay, let's go ahead here. There are a couple of other things that I would like to mention. Just the fact that you have a transpose symmetry allows us to pull this stunt that we did today. And if you start other collision, this is a collision where they were pretty close to each other in velocity. Okay, get an ellipsis just a little bit like the other one inside the one that you started with. If you do a Courant equation, you end up on this ellipse having been on that one before the collision. So that's worth noting again, and again calculating the radius of the collision. So when I'm asking you to go ahead and finish, that's exercise one, is to finish the drawings that you've made today that just have a few lines on it and get some ellipses. I'm kind of looking for this right here. Now, be aware that there's a nice formula here That is the kinetic energy at the beginning and the end minus this lopsided term divided by 4. That gives you this this 1,000, this potential energy that you have. The difference between being elastic and not elastic. If you're elastic, you've got 7,250. If you're elastic, you've got 6,250. The 1,000 is the difference. And that really is what we're going to be calling potential energy. So when these guys go like that, the kinetic energy's gone down to whatever it is on the graph, given by the graph, right? But the whole bunch of molecules, atoms, and electronic bonds and all kinds of things are now in different states of vibration that are higher in energy. And if they're kind to us, they will let you have it all back again as you go to the other side from this point to this point. And that moment when they're in compression, the potential energy is high. Now, we're going to have to go and show that that, in fact, is the same. The energy, the total energy is still potential energy plus kinetic energy. This is the beginning of a proof of that whole use of potential. And notice we have not introduced force yet. But here's where you start to see the potential energy whose derivative is the force. Spatial derivative. Okay. So just to point out the logic that we're getting at here was this way of doing things. Now let's see, something else I want you to do is this thing right here. I want you to go ahead and see what it all looks like if you work in the center of momentum frame. But remember how easy it is for our friend Galileo to do a translation to the center of momentum frame. Down the 45-degree lines you go. And the ellipse that you get when you're done with that better be tangent to those 45-degree lines, and that better be the initial and final in that COM frame. So that's something to look for as you make the drawings that have all of this stuff sort of cataloged in a nice graphic form there. Now I celebrate graphics in this class because physics is getting more and more complicated, and it really doesn't help just to have equations. You need a road map, lots of road maps for those equations. And we'll talk about the Barbachians and other crazy people in physics that made the divorce between mathematics and physics happen. And they were the ones that rebelled against Henri Poincaré. We're going to hear a lot about what he did in classes as we go along here. But they rebelled because he was sort of a Feynman-like character that could just intuit, and of course he was drawing diagrams to do that, various physical truths. And it frustrated the hell out of them. So they demanded of him to spell out all the logical steps, and he didn't want to do it. He said, oh, come on, just do this. And so they rebelled, and they formed a group, the Barbachians, who write papers in which you take your ego away from you by always using Colonel Bourbaki as the author of your math paper. So you're not involved, right? And then figures, any figure, is considered childish and forbidden. Okay. Well, they made some progress in mathematics, but mainly what they did was they broke it off from physics. They made it unpalatable. An interesting history, which I only know little bits of, but it's worth noting because the advisors I studied were very geometrical, and Rick Heller's is simpatico for sure because of his ability to visualize things. Now I would like to pause and say, look, we really are going to set a measure 0 here in our solutions today. In physics, opposite extremes are much easier to analyze, like they have been today, than the generic real world in between. The real world is an ellipse that's somewhere between the complete COM crunch and the nice, don't lose any damage, the initial ellipse, the elastic energy ellipse, okay, as compared to this thing, it only gets to there. And also at some point I'm going to ask you what in the heck happened there, because we are solving a quadratic equation. So remember, there has to be this solution, there has to be one other one. And there it is. But how did you get there? Okay, that's something to worry about that you don't see in the mathematical text. For the geometry, it says, oh yeah, you better think about that. The question is, how do you think about it? Now here, when you want to draw an ellipse, and we're getting close to the end here, but I want to make sure this is clear. This is in the very beginning of chapter 1. Basically what you do, if you find A and B by the algebra, okay, let the algebra do that, then you just draw two circles with those radii. And then draw arbitrarily a radius anywhere. From that point, drop until you are just opposite the point where it crossed this circle. That will be a point on the ellipse. And you can see why that is by just using sines and cosines to describe where the ellipse point is. Now we're going to use this a lot when we talk about oscillator orbits. Harmonic oscillator orbits are ellipses, as are Coulomb orbits, but Coulomb orbits rotate around the focal point. They're lopsided. A harmonic oscillator, I should say a truly harmonic oscillator, is going to be an ellipse centered. So here's our first, that's where this really came from. I put this in as an afterthought, realizing that most people have difficulty drawing ellipses. So this will be for our homework right here. In any case, these are all just pictures of that. This is the graph paper that's available online. If you just take this lecture and print it out, I think we also have the graph paper just in a separate box. We'll try to make a box that has our graph paper in it. So you just go to there and print it out if you need an extra piece or whatever. Okay. All right. At this point, I'm telling you that if you want to stick around, we can have an after-class bull session. Now, how many people here are going for a PhD? Just raise your hand if you're going for a PhD. My gosh, it's everybody.
Sweet.
It's everybody. Okay, that's a record. Okay, you should be aware that 2/3 of PhD is PH, philosophy. Okay, and the question is, should physicists worry about philosophy? This is something Feynman, will worry about, but there's lots of, any of you met Brad Clay, who's not here, he's kind of very, very, very passionate guy. He worries about it all the time. Economics, another one. We had a student who's very good at economics. But mainly, current events and politics, those are really important now. This country's right on the edge of not being a democracy. Okay, that's important. That's really important to pay attention to. What's going on there? What caused that? Okay, so that's one of the things that we're going to have a discussion. This is where, and where does this word liberal come from? It's being told it's bad to be that. Okay. Well, what it is liberal means you liberate yourself from the animal part of you. And you invent things like the 7 liberal arts. First, grammar, logic, rhetoric. That's what drives the invention of these things. Here, this is really algebra. The Mediterranean, the Arabs invented algebra, as far as we can tell. Geometry is mostly a Greek and Turkish discussion. So anyway, this whole thing is so important because if things get out of killer, we're not going to be able to do this stuff anymore. The people that are in there right now just hate science. And they're destroying it. In various cabinet positions are doing this. So I think it's important for us to be educated in more than just the narrow disciplines that we
that we cherish, of course. I mean, it's fine to be able to go in that lower room. Wow, it's really neat that you got there. All hell's breaking loose outside. You're not going to be in that room very long. Okay, with that note, the class is over. But anybody who wants to stick around is welcome to do so. With this 15 minutes or so, just you talking instead of me. Okay?
Yep.